Okay, I think we got a good idea of the change in potential on things. So let's just go ahead and let's go to the slideshow from the current slide so that you can see it better. Okay, positive charges when released, they go from accelerate towards regions of lower electric potential. Negative charges when released accelerate towards regions of higher electric potential. Okay, and then here was, now for a point charge, the electric potential difference of a point charge. Now notice, here's the electric field. Here's and this is going out. This is higher potential here, and it's lower potential as it goes further and further out here. If I go all the way out to infinity, kq over infinity, that equals 0. So the electric potential around a point charge is equal to this. Okay, it's kq over rb. Now, why is it kq over rb? Well, let's take a quick look. Kq over r. Why is it kq over r? Well, look. So if I have a point charge again, we always use by that. I don't know why, but anyway. And I come out here. Now remember, we've got electric potential lines going all the way across. If I come out here, this distance r, then v at that point is equal to k, whatever that charge is, q divided by r. Now, the reason that is, you might be going, well, wait a minute. Do you remember the electric field? E equals k q over r squared. Well, another way to look at the electric field is in volts per meter. Okay, it's in volts per meter. So the voltage is actually equal to the electric field times the distance away from the charge. Oh, so V equals kq over r squared times r. Aha, there it is. Notice electric field times the distance, and so we get kq over r. There's a quick and dirty derivation. So we've got all kinds of equations floating around that right now. We've got the amount of charge is equal to n plus or minus n times the charge of an electron or proton. We've got the first thing was the force of electric field is k q1 q2 over r squared. We'd learned that the electric field can be written in two ways. It's either the force of the electric field divided by one of these charges, or and also so therefore the force of the electric field is equal to Q times E. If we're given a charge that's a distance in an electric field, we can figure out what the force is. Or we also know that E is equal to K Q over R squared. Okay, where this would be my Q here. All right. And we've learned that the electric potential energy, so here's equation 1, 2, 3, 4, 3b, 5, that the electric potential energy is equal to Q times the change in voltage. Okay? So if I decrease my electric potential energy, a negative change in my electric potential energy is equal to my kinetic energy, which is still 1/2 mv squared. So we've already beat that horse a little bit. Okay. All right, good. Good. In fact, I got to modify your homework one more time. All right. So that's what's going on there. Maybe we can blast through some of these slides a little bit quicker. Okay, so if I'm going to out from infinity, then the energy is equal to kq1 q2 over r. That's the energy, because we've got the voltage times q2. Okay. If we're going to do it, build 3 of them, bring them in. So q1 is sitting here. I bring in q2. Well, that's the energy of 1 and 2 combined. And then when I bring in Q3, I've got the energy caused by 2 and 3. and the energy caused by 1 and 3, and then there's no 0.4 here. So what does that look like, actually? What does that look like? It looks like this. When you're building one of those triangles, which we're going to do in class. Do I have that in class? I think I might have a little bit of it. No, I don't quite have this in class yet, but for us to do as an in-class project. But I don't think I think I assigned it as a homework. So if you have Q1 up here, let's say Q1 is positive 2.5 microcoulombs, and then down here the distance of 0.1 meters. You're going to bring in Q2 out from infinity. So remember, when it brings that out from infinity, then that change in potential, one of them, 0. So it comes in. Let's say we're going to bring into this slot a negative charge from way out here. We're going to bring it, plop it down there. And this Q is equal to negative 1.5 microcoulombs. And then at another point here, we're going to bring in this positive charge, Q3, this is Q2, which is equal to, let's say 2.0 microcoulombs positive. Okay? And all of these, they're just a nice equilateral triangle of 0.1 meters apart. Okay, well, I start with my first charge. I just have to start somewhere, so I start with my first charge. I'm going to bring in Q2. Okay, so the voltage that's caused, now remember, he's got electric field lines coming out, but he's also got voltage lines coming down here. So bang, right there. So V1 is equal to K Q1 over R. So this would be K times 2.5 times 10 to the negative 6 over 0.1. That's V1. Okay. Now then, to bring this charge up, the energy required to bring Q2 up here, the energy required, they use U, to bring charge 2 up next to charge 1, that's the way I write it, well, we know that's QV, Q2V1, all right? And so that just becomes whatever we got for V1 times Q2, which is going to be negative. This will be a negative energy because Q2 is negative. So we'd have negative 1.5 times this positive times 10 to the negative 6 times this positive K times 2.5 times 10 to the negative 6 over 0.1. Okay? Now we got to, now look, this guy has voltage coming this way. And this guy has voltage lines coming down this way, changes in voltage. As we follow the electric field, ED, the voltage keeps changing. It's getting weaker and weaker because also the electric field is getting weaker and weaker. That's another reason why the electric field is called volts per meter. Okay. So we're going to bring Q3 up. And let's see the energy required to bring, again, by superposition, U23. This guy creates, so V2, the voltage caused by V2 is equal to K times negative 1.5 microcoulombs over 0.1. So U23 would be Q3 times V2, whatever we calculated there. And then, last but not least, 3 and 1. 3 with 1 would be Q3 times V1. So the total energy to build this thing is equal to U21 plus U23 plus U31. Or you can label them the other way if you want. See how that works? Okay.